In this video, we're going to talk about shifting operations for both unsigned and signed integers, and see how that how we need to do some sign extension for signed values. Let's get started with just the case of unsigned integers. What I'm showing here is both the left shift operation and the right shift operation in C, and you'll notice that we use the double less than sign and the double greater than sign to indicate those, but don't think of them as less than and greater than. Those are just symbols for those shift operators. We just use those because they kind of look like a move to the left and a move to the right. So when we say X shifted to the left by Y, what we mean is we're going to move the bit pattern of X to the left by that many positions, the value of Y. Let's take a look at this example here. Here's the number 6 represented in 8 bits, and we're going to shift to the left by 3. So in this case, the Y value is 3. And what we'd expect to have happen is that those bits would move over by 3 positions. Okay. And you'll notice that the high order 3 bits, the most significant bits, we're going to kind of lose. They're just going to drop off the end. And we're going to have a hole left over on the right of 3 bits that we need to fill, and we're just going to fill that with zeros. Okay? Now, the right shift is very analogous. We're just going to move things over by 2. In this case, we've lost the 1 and the 0, the 2 least significant bits, and we have a hole of 2 on the left to fill in, and we're just going to put zeros in there. Okay, so that's the basic left shift and right shift operator. Let's take a look at another example. But before we do, actually, let me just take a look at these values here. I said that this was the number 6. This turns out to be the number 48, and this is the number 1. So when we did a left shift by 3, what we did was essentially multiply that 6 by the value 8. How did we get 8? That's 2 to the 3rd power. The number of bits were moving to the left. Okay, so we can use shifts to often do multiplications quickly because these are much simpler operations to implement in hardware than a multiplier would be. But of course we can only do powers of 2. Similarly, a shift to the right is a division operation. In this case, we took the 6 and divided it by 2 to the 2, or 4, and we got 1 as a result. Now you see, in fact, we probably wanted 1.5, but we can't represent fractional values. So it got rounded down to 1. Okay. Let's take a look at this other example with the number 242 represented in our 8 bits. When we shift to the left by 3, we are going to multiply that by 8. So we're going to get this value, which is actually the number 144. Well, that's not 242 multiplied by 8. Well, that's a much larger number, and way larger than the 255, which is our maximum value for an 8-bit unsigned integer. So we have an overflow here. So we're going to get a value that doesn't really make any sense. So this tells us that, you know, when we're thinking about doing multiplications using shifts, we better check the number before we shift it to make sure that the result will in fact fit in the 8 bits that we have, or whatever number of bit word we have. If we do a divide by 4 or a right shift by 2, we would expect to get a result of 60.5, and in fact that is the value that we get. This is 60. Of course it got rounded, it's not 60.5. So we have that rounding issue again. Okay, let's take a look now at signed integers, which is a little bit different situation. Here I'm showing a signed integer that's equivalent to the number 98. And we're going to left shift it by 3, multiply by 8. Again, this is way too big a number. We're going to get a result that is equivalent to 16, which is wrong, of course, because we should have gotten 784. All right, so now let's try the right shift, divide by 4, right shift by 2, and we would want to see the number 24.5. Of course, we can't get the 24. We can't get the 24.5. We're just going to get 24, the rounded version of 24.5. Okay. Now, in dealing with signed integers, we have to think about that sign bit. that we didn't have to think about before. So we also have another kind of right shift called an arithmetic shift, where instead of filling in those 2 bits with zeros, we're going to fill in those 2 bits with a copy of the sign bit, the most significant bit. In this case, that turns out to be exactly the same thing. So we don't see any difference. But let's take a look at what happens with a negative number. So down here we have an example with the number minus 94. And again, multiplying it by 8, doing that left shift by 3, is going to yield too negative a number, and we're going to end up with the result of 16, which is just clearly wrong again. And again, that's because now we've had an underflow. We had too negative a number as a result. When we divide by 4, by shifting to the right by 2, we would want the result to be minus 23.5. But if we just fill in with zeros, as we do for our logical shift, then we're going to get a result of 40, which is also clearly wrong. It's not even negative. We've totally lost that sign bit. And that's why we have arithmetic shifts. In this case, again, we're going to copy that most significant bit into those bit positions. So instead of ending up with a positive number, we will still have a negative value. In this case, we have the negative value minus 24, which isn't the minus 23.5 we would want, but again, it's a rounded version of that. Okay, it's minus 24. And one thing to keep in mind is in C, things are undefined if we try to shift by a negative number or by something larger than the word size. The result is undefined, and we could expect to just get junk as a result of that. All right, let's see how these shift operations can be used for more interesting things, though, than just doing basic multiplication and division by a power of 2. Here I'm showing how we can extract the second most significant byte of an integer using shift and masking. All right, so the example we're going to start with is this 32-bit pattern, and we want the second most significant byte. That's the one with the red box around it, and we can get that to all the way over to the right by shifting that value by 16 to the right. Okay, so now we've moved that byte over to the low order 8 bits, and you notice we've padded with zeros on the far left end. Our next operation is what's called a masking operation. We're going to use this bit pattern, which is all zeros except for ones in the low order byte. That's represented by the value 0xFF in hexadecimal. So all ones in the low order byte. And when we mask that, or we'll do a logical bitwise AND with our shifted value, we will just get the result of that first byte, because ANDing, remember, with a 1, the result is just the other value. While ANDing with a 0, the result will always be 0, and we'll just end up with all zeros everywhere else. Okay? So that masking operation is very powerful that way. We can also use shifting and masking to extract the sign bit of an integer. For example, if we just wanted to know if it was positive or negative, what we can do is take the signed integer x, shift it to the right by 31 bits, so that the sign bit ends up in the low order bit position, and then AND it with the number 1, which just has a 1 in that 1 position, right, the low order bit, and everything else will get cleared out to 0. So that's how we can extract the sign bit, and our result would either be 0 if the sign bit was 0, or a 1 if the sign bit was 1. And that makes it easy for us to test if that number was positive or negative. We can also do conditional as Boolean expressions. Remember, let's assume that the Boolean value is either 0 or 1 for now, not anything else. In C, I can do a conditional with an if statement. I can write if x, meaning if x is true, then assign the value of y to a, and if x is false, the else clause, assign the value of z to a. In C, I can also write it in this notation using a question mark, so that I can fit it all into an assignment statement. This says a is equal to either y or z, depending on the value of x. If x is 1, it'll be the value y. If x is 0, it'll be the value z. And we use that question mark and colon to delineate those. Okay, so let's see how we can do these conditionals using shift operations. What you'll see down here is two expressions, one for the if part of the clause and the other for the else part of the clause. And let's look at the one on the left first. You'll notice that what I'm doing is shifting x first to the left by 31 and then to the right by 31. Well, that doesn't seem to make much sense. It's kind of should be ending up back where we started, but in fact we don't, because when we shift to the left by 31, we're losing 31 bits off the end. And then when we shift back to the right, we're doing an arithmetic shift that will copy that most significant bit all the way down through all 32 bits. So our result will be, if we started with x of 0, we'll end up with all zeros. And if we started with an x of equal to 1, we've shifted that one low order bit all the way over to the left, and then arithmetically shifted back over to the right, filling in behind it with all ones. So we'll either have a vector that's all zeros or all ones. And when we end that with y, if it's all zeros, we'll just come up with a bunch of zeros, and that'll be it. And if they're all ones, we'll just have the value of y. On the other side, we're just doing the complementary thing by first complementing x and then doing that shift to the left and shift to the right. So now we'll end up with z if x was 1 to begin with, was 0 to begin with, and all zeros if x was 1. Okay? Then the addition operator will just combine those values, and one of them will be 0. So we'll just end up with the other one. And that's how we get y or z into the variable a. Okay, that might be a little convoluted. You might want to spend some time looking at that. But sometimes you'll see expressions like this in a C program, and it's important to understand where they came from. All right, so that sign extension is really important. And so let's take a look at that in a little bit more detail. What we're showing here is a value of x represented in W bits, and we're converting it into a value of x into something larger than W bits. Let's say we're going from 32 bits to 64. What we're going to do is copy the 31 low order bits just directly down into the larger representation, but then the most significant bit we will copy throughout the upper 32 bits. And we do that to keep the number positive if it was originally positive, or negative if it was originally negative. Okay, so let's take a look at some sign extension examples. Here I'm showing a short int that is represented in 16 bits. Okay, and then we're going to cast it into a 32-bit int. So we're going to go from short int to int, and what we'll see is for the number 1, 2, 3, 4, 5, it's represented in 16 bits with that pattern. And then when we cast it into 32 bits, we're just sign extending that 0 sign bit into all the upper 16 bits of the larger word. For a negative value, if we use negative 1, 2, 3, 4, 5, it's represented by this bit pattern. You can tell it's a negative number because the higher order bit is a 1. And when we sign extend it into the larger representation of 32 bits, we copy that 1 throughout those upper 16 bits. Okay, and so sign extension is used both when we're doing arithmetic shifts to the right, as well as when we're casting a value into a larger bit pattern.